All right. Hey guys. So, welcome back if you've been here before. So just as people start rolling in, I'm just going to introduce myself. My name is Reese, and I'm an instructional assistant for computer science. And we're just doing computer science virtual office hours hosted by Chegg. And these are just like normal office hours, but virtually. So if you have any questions, any comments, any topics you want me to delve into that are related to computer science, just make sure to drop those in the chat like you would in any other office hours. And today's topic is caches. So if you're going over those in any of your computer science classes, like introduction to caches or computer architecture or any other thing that you're just getting like into caches a little bit, we're going to be going over some practice problems with that. And again, if you're joining this and you want other Chegg virtual office hours, make sure to scan that QR code and you can see the full office hour schedule for all your different topics. But as people start to join, I'm just going to start writing out a problem and keep introducing myself as people start to come on. So today with caches, we're going to start off with a direct mapped cache. So I'm just going to write that. So if you guys remember, a direct mapped cache means that every address has exactly one block it can go into in the cache. The direct map cache, and we're going to do 10 blocks in it, or no, sorry, 16 blocks. 16 blocks and 32 bytes are going to be in the block. All right, so that's setting up our first problem. And then we're going to calculate the number of address bits needed for each part of the cache. So as I get that problem set up, I'm just going to introduce myself one more time. So my name is Reese, and we're going over caches for computer science. This is a virtual office hour brought to you by Chegg, and I'm just going to walk through practice problems for caches. So if you're doing those in any of your computer science classes, you just want to learn more about caches, just make sure to drop in and follow along. If you want me to cover any other computer science topics that you're working on in your classes, just make sure to drop that in the chat and we can definitely switch gears. So just make sure to follow along. And again, like if you're confused, if you want me to stop, like if you want me to cover something different, just make sure to drop that in the chat. All right, so I'm just going to get started with this problem. So if there's a 32 byte block size, right? 2 to the 5 is going to be 32. So that means that 5 bits are going to be the block offset. So we'll have a 5-bit block offset. And then if we have 16 blocks, that means that 4 bits of the address are going to be the index of the block, so we know which block it's going to go into. And this is for a direct map cache. And then the last bits, that's 9, all the rest of the 23 bits are going to be the tag. And if you guys remember, the tag is like the identifier of the data. So that means that if your data has a different tag but wants to go in the same block, that means that it's going to shove all that other data out of the block and that new data is going to go in the block. All right, so as we get started with the next problem, again, like if you're just rolling in, my name is Reese, and these are computer science office hours hosted by Chegg. We're just going to go over caches right now, but if you guys are taking any other computer science classes and are struggling with any other topics, just make sure to drop those in the chat and we can go over that. This covers anything like in your first and second year of computer science, any computer science minors, or any self-taught programmers who just like want to learn more about computer science. Any topics that fall into those, just make sure to drop those in the chat. All right, so this is going to be the address breakdown for a direct map cache. But if we wanted to do like a two-way set-associative cache, there's going to be a little bit of a different breakdown. So, okay, so if it's two-way Set-associative. See that? Associative. That means that there will be double as many blocks per index. So instead of 16 indices, there's going to be 8 indices with 2 blocks per index or per set. And that means that instead of having a 5-bit block offset, or we still will have a 5-bit block offset, but instead of having 4 bits of index, we'll have 3 bits of index. And we're going to have 24 bits of the tag. So that's how you answer that question if you get that one. And then after the cache basics of breaking down the addresses, you can start actually mapping in and filling in the cache. So I'm going to start setting up a problem to do that. That's just going to be a little bit more involved. So I'm going to write out some code and we can go through it and actually fill out in the cache. So as I get this problem set up, if anyone is joining within our first 10 minutes, my name is Reese, and these are computer science office hours brought to you by Chegg. So these are just virtual office hours. The computer science ones are every Tuesday, 6:15 to 7:15 Pacific time. And if you have any other classes that you're struggling with, just make sure to scan that QR code and you can see all the other Chegg office hours that we have throughout the week. And if you want help that doesn't fit into those virtual office hours, you can get 24/7 help at chegg.com. And make sure to follow Chegg on TikTok, Instagram, Twitch, YouTube, just to stay up to date with all the things that Chegg has to offer. Okay, so given C code, so we have an array of ints, and it's going to be of size 8, and it has arbitrary numbers in it. We don't care. But we're just going to loop through that array. So as we're looping through it, A is less than 8, we can start to map out where each, and then we're going to have a sum variable, where each element in the array is going to go into the cache. Okay, so we're going to increase sum by each element of the array. Okay. And then the addresses start at the address of array 0 is OX0. And the cache is direct mapped. And it has 4 blocks. Put that over here, 4 blocks. And it has a block size of 8 bytes. All right, so as we practiced before, we have to first break down the addresses and see which part of the address is going to be our block offset, which part is going to be our index, and which part is going to be the tag, so we can start drawing out this cache. All right, and as I start drawing this out, if you just want to follow along and also draw it out, that would be great. And if you ever get confused by anything that I'm writing out, just make sure to drop that in the chat and I can explain it. And if I'm going too fast, just make sure to let me know. These will also be recorded and uploaded to YouTube afterwards, so you can always go through and see what I did and why I did it. So in the cache, right, there are 4 blocks. So these will be the cache indices, 0, 1, 2, 3. And they're 8 bytes. So we're going to have a tag, and we're going to have the data that's in there. And I'm also going to write, no, I'll do that. So this is going to be our cache layout. There we go. Okay. So right before I start this, if you guys are just joining, these are computer science office hours brought to you by Chegg. If you guys have any questions that aren't about caches that are to do with computer science, just make sure to drop those in the chat and we can cover that and switch gears a little. I have a bunch of cache questions prepared today, but this covers anything from any of first and second year computer science topics, any computer science minors, anyone who's just teaching themselves self-taught programming or anything. Just drop any of those questions in the chat and we can cover those. Okay, so as I go through, the first element I'm going to access is array 0, and that has the address of all zeros. So because the block size is 8 bytes, the first 3 bits of this address are going to be the block offset. So I'm going to write that here. I'm just going to write offset. It is 3 bits. It's 3 bits, and then the index, that's going to be 2 bits because there are 4 blocks, and the rest of the address is going to be the tag. All right, so starting off with array 0, the data is the first element of the array, and the tag is 0 because that's everything before the last 5 bits. And the block size is 8 bytes though. So the other thing that's brought in besides array 0 is also array 1. Because when things are accessed in the cache, right, it brings in enough data to fill the entire cache. So elements of array 0 and array 1 are brought in. And then there are a couple questions. So someone's asking why 3 bits for the block offset, and that's because the block size is 8 bytes. So if we want to be able to access all 8 of those bytes, right, we need 3 bits to do it because 2 to the 3 is 8. So like array 1, for example, is going to have the address 0x4, right? And in an array, we have integers of size 4 bytes, right? So this has array 0, and this has array 1, and this is the address 0, and this is the address 4, right? So this bit, right, these last 3 bits, which are 1, 0, 0, tell us that we're accessing the 4th bit of the data. That we want array 1, we don't want array 0, which are 4 bits into the data. Does that make sense? And if we had like the last 3 bits being like 1, 1, 1, we would want the 7th byte of the data. I hope that makes sense. Again, if you guys have any questions, just make sure to drop those in the chat. If you guys want to cover something besides caches, the topic for today that I prepared is caches, but if you guys have any questions that aren't about caches, just make sure to drop those in the chat as well, and we'll just be watching those in the chat for those questions that you guys have. So I covered array 1, right? So that's the next access, is array 1, which also has the tag 0, which is why it's in the same block, and the index 0. And then array 2 has the address 0x8, so in binary that's 1, 0, 0, 0. So that has the index bit of 1, and it still has a tag of 0. So array 2 and 3 are in this block. Okay, and then array 3, the third element, this is 8. That's 12, so that'll be 1, 1, 0, 0. And it still has the index bit of 1, so it's still in there, but it's the 4th bit of the block offset, right? So it's going to be 4 bits into this block is array 3. So if we divide those down the middle, right, this first half will be array 2 and the second half will be array 3. So array 2 is going to be a miss, right? Because we had to pull that data in. But array 3 will be a cache hit because that data is already in the cache. All right, and then as we move on, so we can just kind of follow the pattern. So array 4 will have the address 16, which is 1 0 0 0 0. So that's index 2. Oh, wait, just 1 0. My bad. It'll be 1 with 4 zeros. So that's index 2, and then the block offset is 0. So we have tag of 0 still, and then we pull in the fourth element, the fifth element of the array in there. All right, so that'll be a cache miss, but then when we access the sixth element of the array, that'll be a hit, and so on throughout the cache. So that's how it will be with a direct map cache with a block size of 8 bytes, right? But if the data size was only 4 bytes, then there wouldn't be any hits because we would be pulling in all the data for the first time and it would only be able to hold one integer. Yeah, and the offset is the log of byte. That's totally right. A byte is the array. So the byte, sorry, I'm gonna move this a little bit. The byte is, I think what you're asking, like, what is the array elements? So the array elements is like an array of integers, which are 4 bytes, right? And each block can hold 8 bytes. So these 4 bytes hold one integer, right? And these 4 bytes hold the next integer. So if like the array was the numbers like 0 through 7, then this would hold the number 4 and here would hold the number 5. But which one we access depends on what the block offset is. And yeah, the miss rate's going to be 1/2. And the hit rate's going to be 1/2. So half the time we will hit and half the time we will miss. So these are really good questions. If you guys have more questions on caches, just make sure to keep dropping those on the chat. And I'm going to go with I'm going to do another problem with a fully associative cache now instead of a direct map cache, and we can see like the differences with that. So I'm going to write a problem where we're accessing 2 arrays instead of just 1. So I'm going to leave this for loop there, but instead I'm just going to add one more array. And it's still going to be an int array, but we'll just call it just B. And that'll also have 8 elements. But the address of B0 is going to be, let's look on here. It's going to be 2C. And the address on here is still going to be 0. Yeah, so I'm just going to start off with that, or I'll make it 1C. 1C. Okay, so it's going to start off at OX1C, and then we can see if there will be any hits and misses based off of that. So instead of adding array I, we're going to say B of I equals A of 8 minus I. Seven minus I, sorry, because we want to make sure that we stay within the indices. Okay, so given that, we keep the same offset, we keep the same index, and we're just going to see how that changes with the data and the the accessing of the array. All right, so we're going to keep the cache the same. We can keep the same index, same offset. And this time we are going to try and calculate that hit and miss rate also. And just like as more people join within our first 20 minutes or so, just make sure, like, if you want me to cover anything besides caches, if you're struggling with anything else besides computer science or anything else besides caches in your computer science classes, just make sure to drop those in the chat and I can cover those. So sorry, I'm gonna move these more over here, my bad. So we have the array B, so the address of B0 is going to be 1C, and the address of A0 is going to be just 0. Okay, so starting off with B0, that will be 1C, right? So if I write that in binary, that'll be 1, 1, 0, 1, 0. So that'll be a block offset of 2, and then an index of 3. All right, so we're going to put B0 here. And the tag still 0 because all bits before that are 0, right? And then A, it's not going to access A0 here. It's going to access A of 7 minus 0. So A7 is going to be 7 times 4, which is 28. So in binary, that is 16 plus 28. Sometimes the mental math gets really hard for me. 16 plus 8 plus 4. There we go. Okay, I think that's 28 in binary, but if it's not, please correct me. All right, so that means it's a block offset of 4. But it's also going to have an index of 3. So that means it's going to overwrite this. So we put B0 here, right? It was a miss. And then we're going to cross that off. A still has a tag of 0. Oh no, they overlap enough. Sorry about that. They overlap enough that they're actually in the same block because they have the same tag and the same index. Sorry, I wrote this address wrong. That was super my bad. This is supposed to be 2C. Or not 2C. I'm really sorry. Sometimes I totally mess up and get it wrong. 20. But see, that wouldn't work, right? Because integers, right, have to be 4 byte indexed, and that had a block offset of 2, and that wouldn't work because that was in the middle of an integer, right? Okay, so now B0 has a block index of 2, right there. A0 is here. They both have a tag of 0, and the data is going to go in there. Okay. Or sorry, this is A7. A7, there we go. Okay, and then B1 is going to be 4 bytes off of that. So the address 24 in hex is going to be right here. So B1 will be right there, right? So right now, so far, we still have a miss rate of 1/2, right? But now we're going to go down to A6. So A6 is 24. So that'll be 16 plus 8, like that. So offset of 0, and then an index of 3. So that's right here, right? So that will still have this will still have a hit rate of 1/2. All right, and then we go to B2. So B2 is going to be OX28. So that's 1, 0, 1, 0, 0. All right, so this is the index 2. And that's the index, and that's 4 off there. 2, 0. Oh, sorry, that's 24. 28 is 1, 1, 0. So B2 is going to overwrite this data here and go here. So B2 is going to go right there, and it starts overwriting the data. So I think we have some address overlap, but the point of this, right, and it got a little bit messy, so I'm going to start at a new problem. But the point is that with a direct map cache, you get more misses because it starts overwriting data as you start looping through. So I'm just going to get rid of all this because we're getting super messy on here. All right. Okay. And just take a little bit of a breather because that got super convoluted super fast. So if you have computer science questions that aren't caches, remember to drop those in the chat. And then I'm just going to keep going through with some more cache practice problems. So these will be just a little bit less convoluted, a little bit easier to follow on the whiteboard. So if you want to follow it along, feel free to. If you want to cover other computer science topics, just make sure to ask those. And if you just want to mention what classes you're taking, that would be great, just to drop them in the chat so that everyone knows what skill levels everyone is at, because the classes throughout your first and second years of computer science range really far between just starting out with print statements and then going into data structures and then digital logic and stuff like that. As you progress through, it just what you're learning changes a lot. And there we go. Okay, so I'm writing down these memory addresses. Okay, this is C18. Okay, and then I'm not gonna write that anymore, but it's the same thing. So this is the same thing, but this is 20, and then this is 28. Okay, so this, instead of being a direct map cache like we covered, this is going to be a fully associative cache. I'm going to write that right here. Okay, so a fully associative cache, if you guys remember, means that there are no block indexes, that elements can go wherever, right, in the cache. And that means there will be a lot less misses, but it also is way more expensive to go through that. But we can just walk through that. So it's a block size of 8 bytes. So with this fully associative cache, if we have a block size of 8 bytes, we have an offset of 3 bits. All right, so here, I'm just going to write the offset. This is 0, this is 4, 0, 4, 0, and 4. So these are going to be in the same block, these will be in the same block, and these will be in the same block. However, this fully associative cache only has 2 blocks. Okay, so as we pull these addresses in, right, this will go in 1 block. This data will go here. If we call this 1, 2, 3, 4, 5, 6. 1 and 2 will go in this block. And then it doesn't matter where 3 and 4 go, but they'll go in the next empty block or the least recently used block. And then because 1 and 2 are the least recently used, we just use 3 and 4, it kicks out 1 and 2 to put in 5 and 6. And that's because those don't have any indices, they can go anywhere. But if we start adding indices to this, that means that the data can't necessarily go anywhere, right? It has to go exactly where we map it to. Okay, so if I start writing that out, if we have like an indices with 2 blocks, like if it's direct mapped, right? Then these will have an index of 0. All right, the index is here. These will have an index of 1, and these will also have an index of 0. 6 and 8. All right. No, these will also. No, this is a 0. This will have an index of 1, and this will have an index of 1. And that's a 4. Okay. So this will have the same result, right? But that's only because it's accessed in this way. If it was accessed in a different way, then it would start having a different result. Okay, so these two are 0, 0. Okay, wait, I'm gonna move on to a different set of questions. So I'm gonna get rid of these cache questions, and just move on. All right. In our last half hour-ish, I'm just gonna go over some Boolean algebra practice problems. I'm just gonna switch gears a little bit. So if you guys are just joining, if you're seeing this now, my name is Reese, and we're doing computer science office hours hosted by Chegg. Right now we're doing caches, but we're gonna switch gears a little bit to Boolean algebra. So I'm gonna add that here. All right. Okay, and if you're doing Boolean algebra in any of your classes, make sure to follow along. If you guys have questions about any other computer science topic, just make sure to drop those in the chat. And if you have questions about what I'm doing, make sure to drop those in the chat too. And I always make mistakes, so like double check me, keep me on my toes, just make sure to point out if I ever make a mistake. So with Boolean algebra, right, it looks a little bit like regular algebra, but it has different properties. So we're gonna do a De Morgan's law question. So given this, we're gonna simplify it and ask what is it equivalent to. So if we distribute this not right, De Morgan's law says that not A or B in parentheses is equivalent to not A and not B. And sometimes, it's a little bit confusing when you're first learning Boolean algebra, right? Because, these look a lot like multiplication and just addition. But remember that an OR gate or an OR is the same thing as an AND. Or, sorry, addition. And AND is the same thing as multiplication. All right, so to prove this, right, we can draw a truth table. So it's like if you have this, you might be asked to like draw a truth table. Because in a lot of classes, right, like once you start getting into discrete math, they start asking you to start proving stuff like this and prove through like different methods. And a lot of that is drawing truth tables, right? So first I'm going to draw a truth table for this first one. So this is A, and this is B, and then I'm going to write A or B, and then in the end is not A or B. Okay, so I'll write out all those values. Beautiful. Okay, so A or B here is 0. Here is 1, here is 1, and here is 1, right? So not is the inverse of this. So it's going to go 1, 0, 0, 0 as the equivalent. So that's our truth table for not A or B. And then I'm going to draw the truth table for not A and not B. Okay, so I'm just going to move over here and draw that. So given this same thing, right? I'm not going to draw A and B again, but I'm going to draw not A, not B, and therefore not A and not B. Okay, so not A is 1, 1, 0, 0, which is the inverse of A over there, and then B is 1, 0, 1, 0. Okay, so not A and not B is going to be 1 here, and then zeros for the rest of this. So as we can see here, right, not A and B is equivalent to not A or B. And that's just proving De Morgan's law is this truth table we did. Okay, I'm going to take a sec right now, and you can just look at that. So like for people just joining, for people looking, my name is Reese, and right now we're doing computer science office hours hosted by Chegg. These are just any computer science topics that you're interested in. It covers any first through second year like computer science topics, computer science minors, anyone who's doing self-taught programming. So if you guys have questions like not related to Boolean algebra or caches, which is what we're doing today, just make sure to drop those in the chat. And right now we're covering De Morgan's law and proving it. So we just did that with a truth table. We did it through just a Boolean algebra expression, and now I'm going to do it through gates. So in your classes, you might have heard of bubble pushing. And that means like that you can apply De Morgan's law just through drawing. I'm going to put this. All right, so I'm just going to get rid of these truth tables here, and we can draw these gates out. All right, so I'm going to draw not A or B. So here's A, and here's B, and not is this gate, but it can also just be represented with a bubble. So not A or B is also NOR, so this is just the NOR gate. That outputs this thing, right? And with bubble pushing, what we can do is if we push this bubble through, right, what that does is we now put bubbles right here on A and B, so it makes it not A, not B. And when you push a bubble through an OR gate, it turns it into an AND gate. So now we can see that we just drew both of these expressions, right? And that they're equivalent. And now we can use bubble pushing to simplify other expressions like using gates. So if you guys have any questions about that, just drop those in the chat. I think someone asked what the third expression is. Is it this one? If you can just clarify in the chat what you mean by the third expression. This is like applicable to intro to proofs, but there's like induction and stuff like that if you want me to go over proofs. But this is like one way to prove something. This also applies to like introduction to like digital logic and Boolean algebra. But if you're taking any other computer science classes, we can just switch gears a little bit and go into those problems. But right now we're doing Boolean algebra and caches. So I'm just gonna start doing another Boolean algebra problem, and if you guys have any questions about that or want me to go into more like circuit diagrams, just let me know, and we can do that instead. All right, so we just proved De Morgan's law, and now I'm gonna do a little bit of a trickier one. So let me just pull that up. Okay. So we can do not A and B or A or not B. And now we can distribute this and use De Morgan's law to start like, I'm going to put parentheses around this to start simplifying this and just distributing that not. Okay, so I'm just going to distribute this through. So this is an or statement, right? And as we learned before, not A or B is going to be the same thing as not A and B. So in this case, this big parenthesis, each of these parentheses are A and B. Okay, and then we can use these little ones and distribute the knots there. So inversely, right, not A and B is going to be the same thing as not A or not B. So it goes both ways, De Morgan's law. And then, so we're going to and that with same thing as we did before, not A or B, because it's not B is B. So we have that, and then we can do the same thing with bubble pushing, and we can prove that. I really like bubble pushing because I think it's kind of fun to draw it out and like watch those bubbles push through and become different gates. So if anyone has any questions about that. Someone asked if the bubbles are visual of the truth tables. So a bubble is like a knot, right? And bubble pushing is like moving knots around, kind of like just how I did here. I distributed like a knot, right? So I can show you that. So here we have A or not B. So not B is right here. And then it's an OR gate. So it's like that. And then that is ORed with A and B. So both of those go into an OR gate. And then at the very outside, we have a knot. Okay? So what I did was I distributed this knot right here. So if we do that here with bubble pushing, right, we can push this bubble here and this bubble here, and this turns into an AND gate. So I'm just going to redraw that. So we have our AND gate and a bubble here, and that outputs. Okay, then what I did, right, is right now this is equivalent to this, is I distributed both of those knots on these parentheses. So these two. So I'm going to start with this one, right? So I'm going to push that all the way through here and all the way through here. And remember that becomes, this is an OR gate right now, so that becomes an AND gate. So we get rid of this bubble right here, right, because we pushed it through. And now this becomes an AND gate with a knot here and another knot here. So this is how B, right, instead of not B, just becomes B. So remember how we took it from here to being just B is because these two knots cancel out and we're left with just B and not A. So like that. And then lastly, right, I pushed this bubble through, and this AND gate became an OR gate. So, and those bubbles were pushed through there, just like that. There we go. And then we're left with that last expression, and that's like kind of how to do it more visually. If you're more of a visual learner, sometimes it helps to do it this way. If you like math more and expressions, then doing it that way is great. And then you can finally check your answer right with a truth table to verify that those expressions like do in fact equal each other. On exams, right, I always like to make a truth table because I doubt myself all the time. Only if I have time, but usually on finals and stuff, they have extra time. So coming up on those finals, like no matter how painstaking it is, always draw that truth table if you have time, because then you can check if you made a tiny little mistake. Like if I forgot a bubble, I probably have made a mistake with all these little things. So if you guys see me make a mistake, you have to double check me and just make sure that I am doing it all right. So just let me know in the chat if I made any mistakes. I'm just gonna see if you guys have any questions. Someone's asking about flip-flops. Yeah, I can go over flip-flops next. So, and then some tips I have about learning Boolean algebra is, you can go on check.com for a bunch of resources on like any topics you're learning. That would be helpful. And then also like just practicing a lot, just practicing reduction and just like transitioning from regular algebra to like being more familiar with Boolean algebra, because like you look at this when you're first learning and you're like, oh, that's A plus B, but you have to transition to being like, oh, that's A or B, and there's definitely a bit of a learning curve because it took me forever to just get used to that, but with a lot of practice, that super helps. So if anyone doesn't have any more questions about Boolean algebra, I'm just gonna move on to flip-flops. So I'm just gonna do a quick diagram of a flip-flop here. So we'll call this like in here, and this is out, and then this is the wire, and then we'll call this this out. Or actually, I'm just going to give these one variable names, and that'll make it a little bit easier to track. So we'll call this wire X, this wire Y, and this wire Z. So if you guys are learning about flip-flops in your class, you know that flip-flops always have a clock for each. So this is a D latch, right? This is a D latch, and this is a D latch. And together in one thing, they make a D flip-flop. So a D flip-flop is made up of two D latches. So each of these have a clock. They're connected to the same clock. Okay, so what I'm going to do is I'm just going to draw a little timing diagram, and we can follow like what goes through from X to Y to Z. So just going to get rid of all this Boolean algebra stuff. And first I want to draw the clock. So the clock starts off at 0, goes up, down. Oh no, I ran out of room. We have to move on this way a little bit. I don't want to run off the edge of the board. Okay. And I'm going to say that this is a positive edge triggered flip-flop. So that means that at every positive edge here, and a positive edge means when the clock transitions from 0 to 1. So like it's going positive. This right here is a negative edge. So when the clock transitions from 1 to 0. And what a positive edge triggered flip-flop means is that at every point where the clock rises, the values of the D latches change, or the flip-flop changes. Okay, so here I'm going to have X. I'm going to move this over just a little bit so you can see that just a little bit better. Okay, so here's my value of X, and it's going to start off at 0. It's going to become 1 right here, 1, and then it's going to go to 0 right here. and end off at 1. Okay. So based on this value of x, we're going to fill in what y will be and what z will be. So looking at our diagram, right, we know that it's a positive edge trigger flip-flop. So y is going to start off at 0. We're just going to assume these start off at 0. And then when the clock rises, the value of y becomes x. So here x is 0, so it just stays at 0. And then here, I'm not the best at drawing diagrams, especially on a whiteboard. There we go. Okay. So here, even though x is becoming 1 in this cycle, right, x is still 0 right at this point. So y will stay 0 until the next clock cycle. So here at this cycle, x is becoming 0, right? But we don't care about that for y. We only care that x is 1 when the clock rises. So when the clock rises, y starts becoming 1. And you know, when you're like writing it out, right, you can think of it as happening instantaneously, but these things don't happen instantaneously, so you have to like keep that in mind, you know, like abstractly in your classes, like it happens instantaneously, but there's a tiny bit of delay, which is why my lines here are a little bit slanted, but there's no, like the clock is very linear though. So you can draw these as that, and here, this little triangle is just the delay. So y becomes 1 here. And then here, x is 0. So right here, y transitions to 0 and ends off that way. Okay, we're going to do the same thing for z. So z starts off as 0. Right here, y is 0. So we'll keep going. Right here, y is still 0. So we'll stay at 0. And right here, y is still 0. Y is becoming 1, right? But y is still 0 when the clock rises. So z stays 0. But right here, y is 1. So z rises and becomes 1 right here. But whenever x changes, it takes 2 clock cycles for z to change, as you can see right here. So x changed right here, y changed right here, and z became 1 right here. All right, do you guys have any questions about what I just did? And I can see. Okay, someone had a question about muxes. So with the last 5-10 minutes-ish, I'll just do a little bit of mux practice problems. And if you guys want to go over anything that I did, these are all recorded and published on Cheg's YouTube, so make sure to check those out. And if you want any help with any of your other classes, just scan that QR code and you can see the schedule of office hours throughout the week. And these computer science office hours are every Tuesday, 6:15 to 7:15 Pacific time. So make sure to tune in next time. And if you guys want me to prepare certain subjects for next time, just in the last like few minutes as we're ending, just make sure to drop those in the chat and I will come with practice problems of those subjects next week. Okay, so muxes, if you guys are working on those in your classes, I'm just gonna draw out a mux really fast. Okay, so it's a little trapezoid guy. And we have a selector and we have inputs. So we can calculate the inputs in the selector based off of how many bits the selector is. So the number of inputs is 2 to the power of the number of bits of the selector. So if we had like a 2-bit selector, we'd have, we would say this is like S1 and S0, right? So these represent the 2 bits of the selector. Then we would have 4 inputs. So I4, I3, I2, and I1. All right, so given like a problem of, let's see, we're just doing Boolean algebra. So I'm gonna write a Boolean expression and then we can convert it into a mux. Okay, so but I'm gonna just do a 1-bit just because that'll be a little bit faster. So we're gonna have the mux be 1-bit, and we're gonna say that the selector is A. So, and this will be Y. So our Boolean algebra expression that I'm gonna give is Y equals not A or not B. And sorry, I write my nots in a bunch of different ways. This little tilde is the same thing as a not. There are like 3 different ways to write a not, and it's super confusing. But you'll get used to it. So when I like break down this Boolean expression, right, I'm gonna just write a truth table really fast. So we'll have, and I'm just gonna get down here, A, B, and Y. We have 0, 0, 1, 1, 0, 1, 0, 1. So this is not A or not B. So is A or not B true? Yes. So Y is 0 here. A or not B? No. So Y is 1. A or not B? Yes. So these are both 0. Okay. And if I messed up, please let me know. Do that truth table on your own and just double check to make sure that's right. I think that's right, hopefully. Okay, so if A is the selector, right, we know that when A is 0, input 0 is selected. So what we want to figure out is what is input 1 and what is input 0. So like here, right, when A is 0, we have to see what Y is. And as we can see right here, Y is just the same thing as B. So we can write here that input 0 is literally just B, right? And then here, when A is 1, we can see that Y does not depend on B there. Y is just always 0. So here, our input 1 can just be 0. So our selector is that if A is 1, right, then Y will always be 0, so 0 will always flow through to Y. And if A is 0, right, then we want Y to equal B. So this mux represents that Boolean expression. Okay, so that's like muxes, and so we have covered a really wide range of topics today. So if you guys have any questions about that, just as like we're wrapping up, just make sure to drop those in the chat. If you guys want me to cover any other things next week, just make sure to also drop those in the chat and I can prepare those practice problems. Again, like this, it covers really broad range. It covers anything like any intro subjects, any first and second year subjects. You know, we have like digital logic and pointers and, you know, like print statements. What are they called? Data structures. Like there are just a lot of things that I could cover. So like if you want me to prepare practice problems, just make sure to drop those on the chat. And again, like these are 6:15 to 7:15 Pacific time every Tuesday. I don't know what time zone you guys are in. If you want to drop your time zone in the chat, just do that too. And, you know, yeah, if you want 24/7 help, just go to chegg.com, and my name is Reese. So for the last, how many minutes do we have? Like 1 minute. I guess I'll just erase this and just wrap up. Again, if you guys want any of your other subjects covered, just make sure to scan that QR code. You can see the list of all the live office hours that Chegg has. And yeah, thank you guys for coming. It was great to have you guys in here. Thank you.